So we are going to spend one day today talking about the truss simplification. And
Is that still part of?
yeah, right. And, you know, if it were like, I don't think probably I would talk about the truss simplification on my own, but it is a big part of how other curriculums talk about structures. So I'm going to bring it up just in case it comes up in future classes, but it's a helpful way to sort of think about simplifying things too. And if I have time, I'll talk about how you can use this idea to simplify other structures too. So this isn't something I'm going to emphasize. I really can't imagine putting this on a test or anything, but I'll make you do one assignment today, and I could see putting it on a weekly assignment or something. Okay, so to understand, so today only, it's a special. The truss simplification. And it does simplify problems. So why don't you use it all the time? Because it's very specific what kind of problems it applies to. And we'll get into that more. This simplification is based on the idea of a two-force member. So first we have to understand what a two-force member is. And you might guess that it's a member with two forces on it, and that's correct. So it's a good name in that sense. So a two-force member is one where, it's one where the only loads on a body, on a member, are force vectors at two different locations. So the only loads acting on a body, acting on the member, are force vectors at two different locations. In that case, there are two requirements on those forces that, if we take advantage of them, can make our calculations a lot simpler. The first one is that those force vectors have to be equal and opposite. And I should say, actually, I'm not saying this, but this has to be for static equilibrium for this to be true, which we're always assuming in this class. But the force vectors have to be equal and opposite. If they're not equal and opposite, you have these two force vectors, if one is going, if one is 50 and the other one is 30 or whatever, this thing is going to accelerate. Newton's second law says that. So Newton's second law requires that the forces are equal and opposite. And second, those forces have to act along the line between the two locations where those forces act. So it acts along the line between those two locations. So what that means is usually these members are straight, but they don't have to be, so I'm going to draw sort of a funky thing. So let's say that we have one location here and one location here. And the line between those 2 points is this. And I'm going to copy this. Come on. So copy, paste. Okay, so there's two possibilities. There is these forces could be like this. Or they could be like this. Those are the only two possibilities. And you can think of this one as compression. And this one is tension.
Could you scroll up a little bit?
Mm-hmm. And I want to point out one thing about this. So notice that at each of those two locations, the force vector can be the sum of, any number of force vectors, because always forces acting at a single location really are just a single force. Okay, so at each of the two locations, the force can be the sum of multiple force vectors. So for example, if you had a member like this, you could have F12 here, and F13, and F15, and down here you could have RA and a cable force. That's still a two-force member, because all you have is the sum of force vectors at one location and the sum of force vectors at the other location. So this is still a two-force member. Okay, so then a truss is a structure where every member is a two-force member. So what this requires is this is why this is such a, using the truss simplification, it saves you a lot of time when it does apply, but it doesn't apply to very many practical things. So the first requirement, and the biggest one, is you can't include the weights of any of the members. Because if you have a member that has a pin at one end and a pin at the other end, and then you have its weight acting at the center between them, then that's not a two-force member anymore. And the second thing is you can't have any forces that aren't acting at the joints. So you can't apply any forces at the middle of the beams.
Any non-joint forces or like forces that aren't at the joint location?
You can apply external forces, but they have to be at the joints. So you can't apply any forces away from joints. Okay, so like, when does this ever apply? You know, I mean, like, do you have to be in deep outer space for a truss calculation to be useful? Because if you can't include weights, well, it's useful when your weight forces are very small compared to the other applied forces. Okay, so and we'll do an example, and I'll show you sort of how that works. And so let me give you kind of the rough approach, and then we'll just see it in practice, and we'll see how much it can simplify these calculations. So when you have confirmed, so I just want to be, remind you to be careful about using this. If you use it in a structure where it doesn't apply, your answers aren't going to make any sense. But when you've confirmed that your structure is a truss, isolate the joints. So we've always isolated the members, but in this case, we're going to isolate the joints one by one. Assuming that each member is in tension. So basically, you'll treat each member like it's a cable connecting joints.
If you're assuming that everything's in tension and then you get an answer that's equal, is that just
Perfect. Yep, exactly. Yep. So any positive answers that you get tell you that that member is in tension. Any negative answers you get tell you it's in compression. And then since we're isolating the joints, we're going to assume the joints are particles. And so in particle statics, you only have Newton's second law. So use Newton's second law at enough joints. To solve for all your variables. Okay, so let's do an example. So let's say we have a triangle. And let's say that the lengths of each of these members are 2 meters. And let's say that we have a 1500 Newton force acting at the pin at the top. And let's call this angle 70 degrees and 70 degrees. We're going to neglect the weights. And we're going to calculate the external loads. On each member. I'll call this body 1, this body 2, and I'll call these joints A, B, and C. Okay, so I'm going to start with a free body diagram of the joint B. So there's the joint. And acting on that is a 1,500 Newton force this way. And we're going to assume that member 1 is in tension. So I'll call this F1 pointing that way. And then we're going to assume that member 2 is in tension. So we have a force F2 going that way. Does it make sense to write out a table for this? Well, really the table is only helps you for the moments. I mean, it does help organize things a little. You have it all in one spot, but there's not really any point in doing it if you're only using Newton's second law. So let's figure out these force directions. For F1, you could think of that as like if this is the coordinate system. We know that to get from the positive x-axis to this vector is 70 degrees, and the one we want is 180 degrees from that. So this is 70, this is 180. Those are both counterclockwise, so our angle is 70 plus 180. So that's going to be 250. And then for the second one, we know that this angle is 70 from that 180 line. And then we want the vector that's 180 from that. So I'm going to think of this as our angle is equal to 180 minus 70. So now we're at this one pointing to the upper left. And then I'll add another 180 to that. To get the one going to the lower right. So that theta is equal to 290. You could also just call that negative 70. Question? Okay, so now Newton's second law says F1 times the cosine of 250, F1 times the sine of 250, plus F2 times the cosine of 290. F2 times the sine of 290.
Professor?
Yep.
So we can like it mathematically it works if you put in like a negative angle because the
Yeah.
calculator does that.
Yeah.
Do you want us to make sure it's positive?
No.
Okay.
Yeah, you can do it however it makes sense to you. I just try to bring this up as a way, like if you ever get lost, get turned around, I don't know, I can't see what that angle is. This way of doing it will always get you there slowly and methodically, you know. And then plus 1500, 0. So that gives, so that is negative 0.342 F1, negative 0.940 F1, plus positive 0.342 F2, 0.940 F2, plus 1500, 0, equals zeros. And so the second equation here says F1 is equal to negative F2, or I guess I'll write F2 is equal to negative F1 for substitution. And so then 1500 is equal to 0.684 F1. And so F1 is 2192. It's basically 2193. And so F2 is negative 2193. And I did that really slow in a lot of steps, but that's the end of this problem. You know, still, even going just slowly step by step like that, you know, that would have been a system of 6 equations for 6 variables if we did the full approach. With this simplification, we were able to, you know, just like, we didn't have to write out an augmented matrix and all that stuff. It's like so quick. And now that we have this, like, so I said we wanted to calculate the external loads on the bodies. F1 is in tension of 293, 2193. And member 2 is in compression of 2193. And that's the end of that problem.
So we can only use trusses when the things don't have any mass?
Yeah, if you're told you can neglect the weights, then yeah, you can do it as long as there's one other requirement that there aren't any external forces acting at in between the joints. And then, like, in practice, you know, I mean, this is just a case where, like, say that those things each had a mass of 1 kilogram, okay? Then that 1500 Newton force is a much bigger contributor to the internal loads on these bodies than the weights are. And so that's when you would neglect it. But I want to go through now treat these like they're 1 kilogram, do those calculations, and see how our answers compare to each other. Okay.
I have one question.
Yeah.
If on the free body diagram that we drew at the start, we're acting as if like F1 and F2 are going towards the number, and then we get our answer as positive 2193, and that's an intention going away.
Yeah.
from the number. How does that like, I guess, flip?
Yeah. Well, because then so we only isolated one of these two joints because we got our answer and that was the end of it. But if we isolated A, what we would get acting on A is a force vector RA, since it's a pin. And then since we're assuming that this is in tension, we'd have an F1 like that. And then if you isolated, but then this is isolating the pin, not isolating the body. And so if you isolated so it's a Newton's third law thing. Okay.
How do we know which one is in?
Because you always draw the directions of these vectors, these force vectors, as if it's in tension. So our assumption is always that it's tension, and it's only in compression if we get a negative answer for the variable. Okay.
Can you scroll up a little bit?
Yeah. Farther?
More.
That's the start of class.
A little bit more.
Okay.
Little more.
I think that's it. Oh, no.
Yeah, could you, to the noted.
Wow, I wrote a lot already.
Thanks. Okay. Force can be this under.
My notes for today just basically say, talk about trusses.
In the program, because the H body is 2 meters long, doesn't matter.
That didn't come into it in this. It can come into it, but I guess, it didn't come into it in this, but it'll come into it when we do our full method.
Okay.
Before I do that, let me do one where we have to use like reaction forces with the ground.
But so for
Mhm.
this problem, so the length wasn't actually dependent. Like you never use.
Yeah, only the angles mattered.
Really long, so get the same answer.
Yep. Okay, let's do one. Let's do one that's like, okay, we got a pin here. I'm going to keep these all equilateral triangles just for the geometry. So all these angles are 60 degrees. And all of these are pin joints. And there's a roller here. And let's say that there is a 500 Newton force here and an 800 Newton force here. And all the lengths are 1 meter. We're going to neglect the weights. And we want to calculate the external loads on each member. Okay, well, like when we use the full method that we've been using, a problem like this, you look at it and you're like, oh God, it's going to be like a long afternoon or whatever, But So how many equations would we have using the full method here? 1, 2, 3, 4, 5, so 15, right? 15 equations, 15 variables. But the most equations that we can have using the truss simplification is 2 at each joint. So 2, 4, 6, 8 is the most we can have. And probably we'll be able to skip one of those. I'm guessing, I think we can probably figure out a way that we don't have to deal with the pin joint connected to the ground. So I think 6 is what we're going to get instead of 15. Okay. Okay, so I'm going to call this members 1, 2, 3, 4, 5, and I'll call this A, B, C, D. I mean, we only have, so how many, I'm used to thinking about it in terms of the number of equations, but how many variables do we have? We only have 5 bodies. Each one of those is just going to have a single tension value. So we only have 5 variables. Okay. I'm going to start with a free body diagram of B. We have the 500 Newton force. We have F1, F3, and F4. So Newton's second law says 500 0 plus negative 0.5 F1, negative 0.866 F1. Those are all 60-degree angles. Plus 0.5 F3, negative 0.866 F3, plus F4 0 is equal to zeros. So I guess I'll start my list of equations. So the first equation here says negative 0.5 F1 plus 0.5 F3 plus F4 is equal to negative 500. And equation 2 says negative 0.866 F1 minus 0.866 F3 is equal to 0. And now I'll go to the free body diagram of joint C. So here we have F2 going this way, F3 going this way, F5 going this way. And now for this connection with the ground, you have to consider the load that's applied by that joint. So this is a roller. So the rule for a roller is perpendicular to the surface toward the body, and I'll call that RC. I guess that's our one more variable. So we're going to end up with a system of 6 variables and 6 equations. So Newton's second law says negative F2, 0, plus negative 0.5 F3, positive 0.866 F3. Plus positive 0.5 F5, positive 0.866 F5, plus 0 RC is equal to zeros. So my third equation says negative F2 minus 0.5 F3 plus 0.5 F3 is equal to 0. F5, thank you. And my fourth equation says 0.866 F3 plus 0.866 F5 plus RC is equal to 0. Notice that we could probably get a, yes?
How do you get 0.5?
That's just the geometry. That's cosine and sines of 60 degrees. Yep. We could probably get away without using reduced row echelon form. Equation 2 told us that F1 and F3 are opposites. Equation 3, no. Well, no, that's the only one we have right now. And then free body diagram of D. We have the 800 down. We have F4 this way. And F5 this way. And that is everything. So Newton's second law says negative F4, 0, plus 0, negative 800, plus negative 0.5 F5, negative 0.866 F5 is equal to zeros. And so equation 5 says negative, bless you, negative F4 minus 0.5 F5 is equal to 0. And equation 6 says negative 0.866 F5 is equal to 800. Might as well just do the matrix.
Right, we don't have to find one at A.
Okay, so if we wanted that reaction force for some reason, we would have to do it because we don't have A in there at all yet. But if all we're trying to do is calculate the external loads on the individual members, we already have each one of those represented in at least one equation.
Yeah.
And we have 6 variables and 6 equations. So we have a system we can solve
Okay.
that'll give us all of those. 1, 2, 3, 4, 5, 6. And then our forces, we have F1, F2, F3, F4, F5, and we also have an RC in our equations. And then the constants. So F1 is negative 0.5. F3 is 0.5. F4 is 1. And then was that negative 500? Yeah. Equation 2. F1 is negative 0.866. F3 is negative 0.866. Equation 3, F2 is negative 1. F3 is negative 0.5. F5 is 0.5. Equation 4, F3 is 0.866. F5 is 0.866. RC is 1. And then equation 5, F4 is negative 1. F5 is negative 0.5. Equation 6, F5 is negative 0.866. Constant is 800. So I got F1 is 962. F2 is 19. F3, anyone get this stuff? Negative 962. F4 is 462. F5 is 924. And RC is 1633. And I don't think any of us could have looked at this and said that F1 is in the most tension and F3 is in the most compression. But that's how it works out.
These are the external loads of each body?
Yeah, so then for the external loads, you would just, so member 1 is like this, and it's in tension, so that's just 962, 962. Body.
Doesn't F5 have to be negative?
F5, well, it
has to be.
it is negative. I just didn't write it down. Thank you. And then member 2 is in, it's positive, so it's tension, so it's like this. Member 3 is in compression, so it's like this. Member 4, is that the top one? Is in tension, darn it. So it's like this. And then member 5 is in compression. So it's like that. Any questions?
So out is positive. and
Yeah, positive is out because it's pulling on the thing, like tug of war, and in is squeezing it, like a, what are those things called? Accordion.
Yeah, we could identify tension or compression just by looking at the structure.
There's not like a systematic way I'm aware of. If you do enough of them, you can start to get a better sense. But the more members there are, the harder it is, I think.
So basically, if it's not just like two trusses, then like using this assumption, we're just saving on the moment equation. So we don't have to do the moment equation. But we still have like Newton's second law.
Yeah, right. And you're doing the joints instead of the members. So I think there's usually fewer joints than members, maybe.
Yeah.
So those are the two things that cut down the, yeah. Yeah. Okay.
Thanks, Professor.
Yeah, thanks. Bye.